Well, welcome again to our journey into complex analysis, and we're going to finish off this section with a little bit on the winding number and an application of that again to looking at zeros of polynomials. So we've seen before that this integral of the logarithmic derivative gives us some rather interesting information in that 1 over 2 pi times the integral around some contour of the logarithmic derivative actually gives us the number of zeros minus the number of poles. Well, we can do more than that, because we can also now actually integrate this and say, look, this is going to be some logarithm. So we're going to take log 1 to be any branch of log that's analytic on a small piece C1 of C, of our contour C. So not a closed contour at the moment. C is a closed contour, but C1 is some part of that, some piece of that. And we can therefore integrate this along that. We're going to get log 1 of the bottom from the initial point to the final point. And I can, by the definition of log, this is log of the modulus of f plus I times the argument, where the argument matches the branch. We've taken the logarithm, again from initial to final point. Now if we then sum over consecutive pieces of the contour C, so as this C1 now varies across different pieces of that, and we add them all up, then the log absolute value, log of modulus of z, f of z terms cancel, since we return to the starting point, so initial and final points are the same. But what's interesting is what's happening here is that this is giving us the change in the argument of f as we move around the contour C. And I'm going to write that then as the integral around C of the logarithmic derivative is I times the, I'm going to call this delta of C, delta of f of z around C. So this delta of f of z around C measures the variation of f of z after we complete one circuit of C. That is, what is happening, how many times, or what is happening as we move around this contour C in terms of how this function moves around the origin. So, for example, the f of z then is z cubed. So if we take C to be the unit circle, then what this is measuring is, it says that we're going around the unit circle 3 times because of the z cubed, and the change in angle each time is going to be 2 pi. So 3 times 2 pi is 6 pi, and so I times that should be the value of the logarithmic derivative, or the integral of that. That's in fact around C, not C1. So if we take the logarithmic derivative of this around C, well, you just integrate it as usual, and you get 2 pi I times 3 is 6 pi I, and that agrees, of course, with what we saw up here if we multiply that by I. So this quantity then, 1 over 2 pi delta C f of z, is called the winding number of f on C. It measures the number of times the function winds around the origin as we move around the contour C. Moreover, if f is analytic, then it also counts, of course, the number of zeros in C, because we saw before that 1 over 2 pi I times the integral of the logarithmic derivative gives us the number of zeros if the function's analytic. So I finish with a fairly complicated example of the application of this idea. So we're going to find the number of zeros of this polynomial, z to the 4th plus z cubed and so on, in the first quadrant. And in fact, once we know the number of zeros in the first quadrant, we get the number of zeros in the 4th quadrant for free, because the coefficients are all real. So any root in the first quadrant, its conjugate will also be a root in the 4th quadrant. And here is the worked solution of that. So here's the polynomial. We want the number of zeros in the first quadrant. So to get our hands on the first quadrant, we're going to just take a quarter circle around here. So we're going to go around a quarter circle gamma r, and then we're going to take a little contour that just sends me down from r down to the origin, and another contour beta which sends me back to here again to get my closed contour. And I'm going to let C be the union of these three contours, and I'm going to think of r as being very large. So to count the number of zeros of the polynomial in the first quadrant, we firstly count the number of zeros inside this contour, and then we're going to take a limit as r goes to infinity. So firstly we deal with the easy case. On beta, then z is just x, it's real, and this has got no zeros here. And indeed, as you move from here to here, there's no change in the argument. So the change in the argument of f of z on beta is 0, so there's no zeros there. Now on gamma r, which is our quarter circle, we're going to set z to be equal to r e to the I theta. Now my theta is going to go between 0 and pi on 2. So I can substitute that into the polynomial, and I'm going to factor out r to the 4th e to the 4i theta, which I can take out, and that's what's left after I factor that out. Now the reason I do that is that for this term I can see immediately as theta goes from 0 to pi on 2, I can see what's happening to this, what's the change of argument in this thing easily. So I'm going to write this as r to the 4th e to the 4i theta times 1 plus some function g. And I want to just get an idea of the size of this g. Well, the modulus of g is less or equal to the sum of the moduli of each of these. And the moduli of each of the e to the I theta terms is 1. And I can, because r is bigger than 1, I can replace all of the terms with just an r. And so that's 4, 5, 6, 11, 12 over r for large R. And it also means that the modulus of g is going to 0 as r goes to infinity. So essentially we're getting this, the change of argument is going to be the change of argument in this, plus the change of argument in this 1 plus g, so I can then take the argument of each of those. So the change of argument as I move theta goes 0 to pi on 2 is going to be 4 times pi on 2, plus there's going to be a little bit where this delta 1 goes to 0 as r goes to infinity. So I'll write this as 2 pi plus delta 1. So what that means in physical terms is that as I move around that quarter circle gamma r, the change in the function p of z is moving through 2 pi plus a little bit around the origin. It's moving through that angle around the origin as I move through gamma r. Now finally, in the most fiddly part is what's happening on the contour down here. I'm going to look at what happens on minus alpha, and then just put a minus in front, because it's easier to move from 0 up to r than it is to go the other way. So on minus alpha, x is equal to 0 and y is some real number between 0 and r. That is, I'm putting z to be equal to 0 plus iy in. So I substitute that into the polynomial over here. So I'm putting z is equal to iy into here, and I just pull off the real parts, and then I get the imaginary parts. Now happily both of these things factorise nicely, so I get this factorisation here, and I'm going to call that capital X plus capital IY. And again, we want to know what is happening to P of Z as I move up this contour, and we'll take the opposite, take a minus of it. So what's the change in argument of P as I move up here? And to do that, we're going to look at the positions of X and Y as Y varies from 0 up to infinity. So I make up just this little table here. So if Y is between 0 and 1, looking back up to here, we can see that this term will be negative, this will be negative, so overall X is positive. if y is between 0 and 1, then this will be negative, positive, and so overall positive. So we're starting off somewhere in the first quadrant. We're starting off somewhere in the first quadrant. And indeed, if y is 0, we're starting off actually on the x-axis. So for y in this range, we're starting off at 0, we're somewhere in here. Now, if y is between 1 and root 2, then in that case, this term will be positive, this will be negative, so this is overall negative. And if we're between 1 and root 2, then this is positive, this will be negative, and overall going to be positive. So that means if y is in this little section, then in the capital XY plane, we're over here somewhere. X is negative, y is positive. So we're moving in some way, it won't be a circle, but we're moving sort of wandering around here, and we're ending up somewhere in here. And of course, at root 2, we're going to be actually down here on at that axis, because we can see we'll get the y value is 0 at root 2. Similarly, if we go between root 2 and 2, these are all the critical points, of course, of the polynomials here. So between root 2 and 2, same argument, the x is negative, y is negative. And again, at 2, x will be 0, and so y will be down here somewhere, so it's wandering down here. These won't be circular, but there'll be some sort of curve wandering down here. And in between, we're in the third quadrant. And finally, if y is bigger than root 2, then again x is positive, capital X is positive, capital Y is negative, and so we're going to be around here somewhere. Now, we're not going to get back to the origin, but we're going to be moving along in this direction somewhere. We're somewhere in the fourth quadrant. Now, this was going along alpha the wrong way, so the change in the argument then is going to be, well, if we did in this direction, the change of argument's 2 pi, and then it's going to be minus something, minus a little bit. We're taking minus that, so we're going to be minus 2 pi plus some number delta 2, with delta 2 again is going to go to 0 as r goes to infinity. So if you're looking at the angle between wherever this is, the angle between this and this point as this moves off to infinity is going to be becoming smaller and smaller, so it's going to go to 0. Finally, if we put all that together, then this says that the change in argument of p of z as we move around this contour C, well, we just add up all the bits, and the 2 pi's and minus 2 pi's cancel, and the delta 1's and delta 2 go to 0 as r goes to infinity. And that tells me this polynomial then has no roots, because 1 over 2 pi times this gives me the number of roots. And so 0 over 2 pi is still 0, so this has no roots in the first quadrant, and hence it's got no roots in the fourth quadrant, since, as I mentioned before, the coefficients are all real. And that's a nice example of how we could use this logarithmic derivative and this winding number, plus some analysis, to pin down the number of roots of various polynomials in various quadrants by using this sort of argument. And this is the last video in this series of Journey into Complex Analysis.